Okay, good evening. So this is the last class for this semester. I'll teach today about control. But I have a few announcements before that. The first is that so next week we will not have a class. Instead, we will have a class the week after, 22nd of July. Same time, I hope that same place, also here. It should be. I asked for this room. Hopefully I'll get it. And it may be longer than usual class. And everyone must attend this class. Therefore, it's now recorded. In this class, you'll present the second part of the work, of the homework, of the mini project. You'll show the main idea of the paper that you reviewed or your own research. You'll present the main ideas and your simulation. That's the idea. Each group will get 10 minutes for presenting. It should be such that everyone could learn from this and understand the algorithm or what you did. And in addition to this presentation, I'll open how do you call this? An assignment in Moodle that you can submit there the work. You'll submit one PDF file. And in this PDF, you'll show the two parts of the work of the mini project, and also you'll you'll open a Google Drive or something like that, a shared drive, and you'll put a link in the PDF file, so I can copy it. I can copy it to the browser and see the whole directory with the simulations, videos, source file, code, everything will be there. All the supporting material that you have to submit will be in this directory that will be as a link in the PDF file. Please note that you'll and pay attention to that you'll give a permission for everyone that has the link to view the file, to view the directory. Okay, so check this carefully. So I won't need to ask for permission and so on, and it will take longer to get everything. So so give permission in advance. So that's it. Any questions for that? Okay. So we'll start this class with a material about control, and that will be the material that will conclude the material of the course. If we'll have more time today, I'll show you a little bit of other things that may be useful or interesting for you, but they are not part of the curriculum. So I'll share the screen. Okay. Do you see the screen?
Yes, Anand.
Okay, good. So no, that's not what I wanted to. That's not the no. This is not. No. I wanted to show something else. Yes, this one. Yes, just a second. Okay. Now it's the correct one. So we talked about the dynamics of the system, Lagrange equations, in which we develop the Lagrange equations. We talked about the kinetic and potential energy, from which we develop the Lagrange equations, and we get the equations of motion in a matrix form. We define the state variables, and we represent the equations of motion in the state space representation, in which we get the full dynamics as as x dot equals f of x, where x are the state variables and f is the whole dynamics of the system. Now we can discuss Sontag formula. Sontag formula is a way to develop a control method, control law, for stabilizing a dynamical system. So we want to stabilize the dynamic system x dot equals f of x and u, where u is the input variables. And we want to have a control law u, which is a function of x, which is alpha of x. So the control law will depend on the state variables. So each time we apply control torque or force, it will depend on the state of the system. So now we have the full dynamic system after we applied the control law, and we substitute u into the dynamical equation, and we get x dot equals f of x and alpha of x. And now we want to find a control loop such that it will be stable. It will be stable if we can find a Lyapunov function, a control Lyapunov function, such that v dot, v is the Lyapunov function, and if we find v of x, Lyapunov function, such that v dot is smaller than 0, then the whole system will be stable around the equilibrium. We assume here that the equilibrium is in x equals 0. So v dot is dv to dx times x dot, and x dot from the dynamical system is f of x and alpha. So we have dv to dx times f of x and alpha, and this whole term must be smaller than some positive, some negative function, which is minus w of x, and w is a positive definite function of x. So the controller u equals alpha of x should be such that v dot will be smaller than minus w of x, where w is positive. So we'll see an example. If I have a simple dynamical system with only one input and one output, only one state variable x, and x dot equals cosine x minus x to the third plus u. And we need to find some u, which is alpha of x, that will stabilize the system about x equals 0, x star. This is the equilibrium point. And you see, okay, this will be the equilibrium point. So in feedback linearization, if we want to use feedback linearization, we use u equals minus cosine x plus x to the third minus kx. So when I substitute this u into the dynamical system, cosine and cosine are canceling each other, x to the third canceling each other, one is minus, one is plus, and I'm left with x dot equals minus kx, and if k is positive, then the system will be stable. That's the meaning of feedback linearization. I use the feedback in order to cancel all the nonlinear parts, cosine and x to the third, and I left with only a linear system of x dot equals minus kx. And in that case, I can choose v to be half of x squared, and v dot is actually the derivative of this. The derivative of half of x squared is x, and then I substitute x dot, and x dot, when I substitute the u into the dynamical system above, it's just minus kx. So v dot will be minus kx squared, and this is always negative, and therefore the system will be stable around the equilibrium, which is x star equals 0. But the question is whether I need to cancel all the nonlinear parts. Sometimes the nonlinear parts are good, are stabilizing the system. So I don't need to cancel them, maybe. So maybe I can use them instead of canceling them. And maybe I can set another feedback law, another control law that won't cancel them. So let's try something else. If I cancel only cosine and I do not cancel x to the third, what I get here? So I'll get, now u will be minus cosine x and minus kx. When I substitute this into this here on the top, into this dynamical system, x dot equals cosine x minus x to the third plus u, I'll get minus x to the third minus kx. So I cancel only the cosine term and not the x to the third term. So again, I'll choose as a Lyapunov function a half of x squared, as you can see here. And the derivative of this, of half to the x squared, is actually x. So I'll get dv to dx is x. And now I need to multiply by x dot. X dot is the dynamical system after I substitute u. So cosine cancel each other, and I'm left with minus x to the third minus kx. This is x dot. But this will be minus x to the fourth minus kx squared. And since I have x to the fourth and x squared, they are both positive. And I have minus before of them, so this is strictly negative. So now I can stabilize the system. And it is asymptotically stable, and I can stabilize it using a controller which is much simpler. And we actually use parts of the dynamical system to stabilize. The x to the third is actually a stabilizing term and not something that will destabilize the system. And now also, since I have x to the fourth in v dot, the rate of a convergence to the equilibrium point will be faster because it's x to the fourth. It's actually getting down to 0 much faster. So now I can formalize the general form of Sontag formula. So we assume a nonlinear system of the form x dot equals f of x plus g of x times u. U is the input, and f and g are some functions of f, some nonlinear functions of f, where f of 0 is 0, because we assume that 0 is the equilibrium point. If not, we can just substitute x plus something or minus something in order to move the equilibrium point to 0. We have a candidate Lyapunov function v of x, and we look for a control law in the form of u equals alpha of x, such that v will be positive definite and v dot will be negative. So what is v dot? V dot is dv to dx times x dot. And x dot we already have from the dynamical system. It's f of x plus g of x times u. So we have dv to dx fx plus dv to dx gx times u, which is alpha. So dv to dx g times the alpha. And now we want alpha to be strictly negative. Therefore, if we choose alpha such that it will be 0 for dv to the x times g shall x 0. Therefore, this whole term here will vanish, and we'll get only this term. Or for when this term, when dv to the x g of x is not 0, we'll get this whole term. And when we substitute this into v dot, into the term of v dot, pay attention that we divide everything by dv to the x g. So this part is canceling this part. We have dv to the x f of x, which is this. This is minus, this is plus. So they cancel each other. And we have minus this whole term, which is under the square root. And under this, we have something which is square and something that is to the fourth. So this whole term will be negative. We'll get what we have at the bottom, that v dot is minus the square root of dv to the f times f to the square plus dv to the dx times g to the fourth. And this is always negative. So this is actually Sontag formula, and it is negative. It has a Lyapunov function which is positive, and its derivative is negative everywhere except of the 0, and therefore the system will be stable. So let's use this formula for the dynamical system that we saw before.
Amir, can I ask a question before the example? So I might have missed it because I had to join late, but what if your dynamical system has multiple states that you want to control and not just one? And let's say also multiple PID controllers.
Sure.
The control law will be different for each state.
So alpha will be a vector, and this whole solution will be for multiple terms. So it will be all vector-wise, the same thing.
Okay, got it. Thank you.
We'll have dv to dx times f of x, and alpha will be a vector. And G will be actually a row, a vector, or a matrix, can be a matrix.
Okay, thank you.
So let's get back to the example that we did before. I put on the side the Sontag formula on the right side, so we can remember what it is. And now again, we have the dynamical system x dot equals cosine x minus x to the third plus u. We need f of 0 to be 0. And therefore, we choose u to be minus cosine x, so that f of 0 will cancel the part of cosine x plus alpha of x. And we substitute back to the system, and now we have a dynamical system, x dot equals minus x to the third plus alpha of x. So now we can choose a Lyapunov function. Here we didn't talk about the Lyapunov function because we have dv to dx. So we actually select the Lyapunov function half of x squared. And in our case, x dot equals f of x plus gxu. So in our case, f is minus x to the third and g is 1 because we have only u. So dv to dx is actually x times f of x is minus x to the fourth. And dv to dx times g of x, so dv to dx is again x, times g of x is, g is 1, so it's x. So now we can substitute everything into the formula of u. U is, everything is divided by dv to dx times g, which is x. And on the top, we have dv to dxf, which is minus x to the fourth, plus square root of dv to dxf to f square, which is x minus x. Yeah, everything should be, so it has to be plus x to the 8 plus dv to dxg, which is x, and all of this has to be to the fourth. So I have x to the 8 plus x to the fourth, and all of this under the square root. I can reorganize this, x to the 8 plus x to the fourth as x to the fourth times x to the fourth plus 1. And therefore, I can divide everything by x. So I have eventually x to the third minus now x to the fourth, square root of it is x squared, divided by x is x, x times the square root of x to the fourth plus 1. And therefore, this is alpha. And therefore, our controller is u equals minus cosine x plus alpha. So we have u, which is minus cosine x plus alpha, which is x to the third minus x square root of x to the fourth plus 1. And this will stabilize the system around the equilibrium. Yes, so this is exactly the same. Yeah. And we have u, and the system is asymptotically stable. So that's the idea of Sontag formula and how to stabilize a non-linear system with a non-linear controller, how to shape the controller. But we can shape the controller such that the system will navigate along a trajectory that we want. And for that, we are using the artificial potential navigation function. And we use these functions to navigate the system and also to control the system. and I'll show you how this is working. So first, the main idea of potential functions, potential field for path planning. This method was started by Osama Khatib in 1986. So the robot is now treated as a point under the influence of an artificial potential field. So it's not a real potential field, it's just artificial in the brain of the computer. And the robot is assumed to be a point in a configuration space, which the configuration space can be in any dimension. Here I'll show in 2 dimensions, but it can be even in higher dimension space. And we have the goal where the robot, the start point, the goal point, and we have a configuration obstacles that the robots need to avoid them. So it operates in a continuum. It's a continuous space. It generates the robot movement, and it is similar to a ball rolling down the hill. So if I can imagine the artificial potential function as a hill and valleys, or actually one valley and some hills, so it's like taking a ball and let it go down the hill to the valley, and the valley is the goal position where the robot should get to. So it actually generates a path and a control signal to the motors of the robot in order to get from the start to the target without hitting the obstacles. So the goal generates an attractive force that attracts the robot or the ball that's rolling down the hill. So it attracts it to the target position, and the obstacle generates repulsive force that repel the robot from them. You can see here some pictures. So if I have a 2-dimensional configuration space, and I have a start position and a target position, and I have some obstacles, I can generate one potential function with a minimum at the target and some high potential over the obstacles. And therefore, if I start from the point here and I roll down the hill, I'll go just around the obstacle and get to the target. Yes, local minima is the main problem of that, and there are a few methods how to avoid them. Let's talk about this just later on, okay? So we model the potential. Why is that? We model the potential, the artificial potential function is the sum of 2 potentials. One, and this is called the navigation function. It's the sum of the forces on the robot. So first, we want to attract the force attractive force that attract the robot to the target. And for that, we use something very similar to a spring, a force which is equal to minus kx. So it's exactly like the force of a spring that attracts the system to the target, to the here x equals 0. So like Hooke's law, it's linear. And for repelling from the obstacles, we actually build a mountain over each obstacle. And in our case, we use something like the repulsive force of electrical charge, which is proportional to Q1, Q2, these are the two charges, divided by R squared. So the important thing here, this is a constant, and the important thing is that it is divided by R squared. So and R is the distance from the obstacle. So as R getting lower, getting smaller, and we are getting closer to the obstacle, therefore the mountain goes higher as we get to the obstacle. So this is the attractive force. And this is a vector field that has like an arrow at every point that attract to the goal. And the repulsive force actually is again a vector field that points out from the obstacle. And for the navigation, we have this vector force, which is a combination of the repulsive part and the attractive part. And therefore, if we go along these arrows, we'll go around the obstacle and get to the target. But now we want to formalize this. This is the idea. I think we'll take a break just before that, and we'll continue after the break. Okay. Okay. Okay, we continue. So, yeah. So now we want to prove that the system actually is stable and it will reach the minimum of the potential function. So we set a scalar function u, which is also the Lyapunov function, and u will be high on the boundaries of the obstacles and has a unique minimum at the global configuration Q desired, or the goal configuration. We have the dynamical system as we saw before of a robot in the matrix form, and we have a control input to the motors of the robot, which is the minus gradient of u minus kd q dot, which q dot is actually the velocity of the robot. So what is that u? U is actually the the potential function, which is combined of the gravity potential function and the navigation potential function. This is UG plus U. And G itself, the vector G, which is the effect of the gravity of the dynamical system, is actually the gradient with respect to Q of the potential energy of the system. So we set a total potential function, which is UG plus U. And the equilibrium is the extremum, actually the minimum of U tilde. That is where the gradient of U, which is the gradient of UG minus the gradient of U. This is the total force applied on the system, is 0. So that's the definition of the equilibrium point is Q such that this thing is 0 because here this is multiplied by Q double dot, which in equilibrium is 0. This is multiplied by Q dot, C is multiplied by Q dot, which is also in equilibrium 0. So we need G to be equal to tau, and this is actually G is minus U, and tau is minus U, minus gradient of U, and this is actually the total of the force, which must be 0 in equilibrium. So now that we have an equilibrium point, we want to see if the system is stable, and it will reach the equilibrium point. And the equilibrium point, we set it such that it will be in the global minimum of the potential function. So we set the candidate Lyapunov function or the control Lyapunov function to be the total energy of the system. It will be the kinetic energy, half of Q dot transpose M Q dot, plus the two potential functions UG and V. This is the total kinetic energy. Then we take V dot. V dot is actually the derivative of that, of V. So we have, instead of half, we have Q dot transpose N Q double dot, and half Q dot transpose N dot Q dot. This is the derivative of Q dot transpose N Q dot. And we have the derivative of UG, which is Q dot transpose gradient of UG, plus the derivative of U, which is Q dot transpose gradient of U. All the gradients are with respect to Q. So now we can collect all the terms. Q dot transpose we have on the left. So NQ double dot is what you see here, tau minus CQ dot minus G. So we have CQ dot minus G, and tau is the gradient of U minus KdQ dot. This is tau. And okay, and then we have the Q dot transpose N dot Q dot and Q dot transpose UG and Q dot transpose gradient of U. And you see that CQ minus CQ dot plus N dot Q dot, this term is skew symmetric, antisymmetric, and therefore the quadratic form of Q dot transpose this and Q dot on the right is actually 0 because we have M dot minus C. Actually, half M dot minus C. So we have like M dot 2C, which is an antisymmetric matrix. And therefore, this term with the M dot is 0. Next, we have G here, and we have the gradient of Q dot transpose gradient UG, which is here in minus, there in plus, so they cancel each other. We have the gradient of U, and we have the gradient of U here, so they cancel each other, and we are left only with Q dot transpose minus K d Q dot, and that's it. And this is always, and KD is a positive definite matrix, and therefore this is always smaller than 0, and we can apply LaSalle principle and show that the system is stable and converge to the minimum, to the global minimum of U tilde. So now how do we shape U? Until now, it was just an arbitrary function, but we want to shape it in such a form that U will shape such a force that will attract the system to the global minimum and repel the system from the obstacles. And if we are using like a mobile robot, if it's a robotic arm, we can apply U as a torque, or F will be a direct torque to apply to the motors. If not, if it's a mobile robot, we can set the speed dx dy or the torques tau x tau y proportional to F, which F is the gradient of U. And U is composed of U attractive and U repulsive. Now, how do we shape the attractive potential? So the attractive potential can be a simple quadratic function, like a paraboloid. As you see here, some coefficient times Q minus Q goal to the square. So it has a global minimum at the target. And the attractive force is actually the derivative of this potential, which is K attractive times Q minus Q goal. So it's a force that is pointing towards the target configuration. So the attractive force, we can set it as, again, as the gradient of the potential as we saw before, but we do not want it to be too big outside, too far, and therefore we kind of limit it. And we have a bound to the attractive force very far away, which is D star, and the form of U attractive is like this, and the force itself, you see, if we are close to the global minimum, is linear to the distance. If we are far, so it is constant with the direction pointing to the target. So this is actually a vector that points to the target, but we divide by the length of this vector, and therefore this is only a direction vector, a unit vector in the direction pointing towards the goal, and this is a constant, and therefore far away it's just a constant force that directs the system to the goal, in order not to saturate the motors, not to get to the maximum torque. So this is the attractive force. Now the repulsive force. The repulsive potential field is built like this. It's like 1 over r squared, as you can see here. Rho is the distance from the distance from the obstacle, and 1 over rho squared, this is the potential, and therefore the force itself will be 1 over, yeah, it's here, 1 over rho squared. If rho is greater than some rho 0, some is smaller than rho 0, then it will get very high, and if rho is bigger than rho 0, so I'm far away, the robot is far away from the obstacle, and therefore the repulsive force is going to 0. So instead of going all the way away, we just close the repulsive force at a certain distance from the obstacle. So we get this repulsive force, which is proportional to 1 over rho squared. Okay, but the problem is when rho is going to 0, when I'm going closer and closer to the obstacle, as you can see in the graph, the repulsive force getting higher and higher. And I cannot apply an infinite torque or an infinite force. So that's a problem. I need to limit this to the maximum force that I can apply. So instead of using this repulsive function, potential field, I have a function sigma that maps numbers from 0 to infinity to the range of 0 to lambda, lambda a constant. And that sigma function, when applied on any x, any function, it's x over 1 plus x times lambda. So when this goes, when sigma, the x goes to infinity, then this is actually 1 and we get lambda, according to L'Hopital. And so I can use this sigma function and apply this on the repulsive function. So I get the number from the repulsive function as x, then generate what sigma of x, and that will be q. That will be the potential function, and then I can limit the potential field to be limited to lambda. and not goes to infinity. So instead of the potential near the obstacle to go to infinity, now it gets to lambda, and the potential function is applied only within a certain distance from the obstacle, not all the way, but only in a certain distance. And then when I take the repulsive force, as you can see here, and add it to the attractive force, attractive potential, actually, the attractive potential plus the repulsive potential, I'll get something like that. And the force that I need to apply on the robot is the gradient of this potential function. And then, since we have at the minimum of u, we have an equilibrium, which is stable. We just proved it, that is stable. Therefore, it is guaranteed that no matter where I start, I'll get to this global minimum. So, as you can see, I have an environment with some obstacles and start in target position. Actually, start in target position. I have an attractive potential. I have a repulsive potential. Then I combine them, and I have this attractive and repulsive potential. From that, I take the gradient, which is the vector field that you can see here, with the repulsive forces and attractive forces. And when I apply this to the robot, this gradient force field, then the robot will go and select the path such that it will avoid the obstacles and get to the global minimum. So it looks very good, but there is a problem. And the problem is that we may have local minimum. And if the robot is stuck in local minimum of the potential function, as you can see here, if I have a non-convex obstacle, so I get here something like a local minimum, and the robot can get stuck in this local minimum. And that may be a problem. So there are several methods how to deal with that. If you get to a local minimum and you get stuck, then you do numerically fill this local minimum like water until the water finds a way to go around. So you actually fill this part, and then when you get to a certain height that there is a way, then you go away, or you apply something like random walk nearby, and then find a way out of the obstacle or something like that. There are several ways how to solve this, but this is a major problem. What? It's not the shortest path. It is a path. It is guaranteed to find a path in certain conditions. It is directly finding a controller to a dynamical system, which is an advantage, a stable controller, but it's not the optimal shortest path. It is a path that avoids the obstacle, but it's not the shortest one. In practice, you can apply this directly online during the motion by calculating the distance using something like a range sensor, LiDAR, or something like that, and find the distance from the obstacles, and according to that, calculate the repulsive function directly. And you can see here a simulation of the robot motion, such that it is avoiding the obstacles, and there is the potential function on the right, and you see how it loses height and get to the global minimum. That's the idea. With that, we conclude the part of the control and also the potential function. And this is actually the whole material of the course. I want to show you one more thing, and then we'll discuss what's more. So it won't take a long. Yeah. Just a second. This one. And I hope it's this one. Yes. Okay. So I want to talk a little bit. It's a long presentation. I won't show everything. I'll show only the main ideas about quaternions. We talked about rotation matrices to represent rotations, but there is another way how to represent rotations, and this way is quaternions. It's a very common way, and it avoids a major problem in the what we call the rotation matrices, the directional cosine matrix, which is called gimbal lock, when several axes, like if I represent a matrix in roll, pitch, and yaw, several axes are combined and look at the same direction, so the rotation matrix loses a rank, and I cannot I don't have the inverse, and it's a major problem. And the quaternions avoid this gimbal lock problem. I think I can find, no, I won't show it now. There are two sides, actually it's one side that show very nice what are quaternions, and there's also kind of an online course, online class for that. It's about half an hour, so I'll do it much shorter than that, but if you want, you can look there. So quaternions comes as an extension to complex numbers. So I just remind you what are complex numbers. Complex number has a real part, an imaginary part, such that I, the imaginary part, I square is, or I is the square root of -1. And the complex number, regular complex number has the real value Cx and the imaginary value ICy. I can represent it as in a Cartesian form or in a polar form, which with a magnitude and an angle. And we have the conjugate to the complex number, which is taking the minus of the imaginary part or taking the minus of the angle. Okay. So addition of complex number. So adding to the real to the real, the imaginary part to the imaginary part. Multiplication is a little more complicated. So multiplying A, B, it's like this form, or multiplying the length and adding the angle in the polar way. So if I have a point in the imaginary, in the complex plane, and so translation of this point is just an addition. Scale is multiplying by a scale factor S, and rotation is changing its angle. Is actually multiplying by a complex number with a length of 1 and an angle of theta, and therefore it's rotate by theta. And we can do this. Component form is identical to matrix rotation with this exactly the same. So I won't get into this. Okay. What are quaternions? So quaternions are just vectors, but they were invented before the vectors and matrices and all the linear algebra was invented. It was invented by Hamilton in 1843. He didn't have the vector algebra and vector and matrices, and therefore what he knows how to represent vectors was using complex numbers, but complex numbers just in 2D plane, and he wanted a 3D plane. So he extended the complex numbers into a vectors. So first, here it says the rank 0 tensor is a scalar, rank 1 is vector, rank 2 is a matrix, and so on. No, what happened? Why it's not? Why? Okay. So what are quaternions? Quaternions has a scalar or real part and imaginary part. But the imaginary part is a vector. It has x times I, y times j, and z times k. So I have like an xyz vector with 3 imaginary parts. One is I, j, and k. So it's actually a 4-dimensional vector. This Q, but it behaves like a complex number, with 3 parts imaginary and 1 part real. So if I want to represent quaternion in kinematics, in rotations, so in rotation, if I want to rotate around some arbitrary axis, n, which is a unit. Actually, no, it's not a unit. The whole system is a unit. And n is the direction of rotation, and theta is the angle that I rotate according to right-hand rule. The angle that I want to rotate around this axis. Then the quaternion that represents such rotation has a real value of cosine theta divided by 2 and an imaginary part of n times sine theta divided by 2, and n is a unit vector, and therefore the whole quaternion is a unit vector. It has a magnitude of 1. So what are the I, J, K imaginary parts of the quaternion? They behave exactly like complex numbers. So I squared is -1, J, K also are -1. Also their multiplication, I times J times K. And Ij is K, Jk is I, Ki is J, and it is like a cross product. So the quaternion is represented with W, the real part, and X, Y, Z, the imaginary parts. The conjugate of the quaternion is taking the minus of the imaginary part. This is how we add quaternions. We can do this also by components. We can do multiplications of quaternions. So if I multiply, if I multiply, I can do it by components or in vector form, and you can see here the dot and the cross. And actually, Hamilton used this in order to get cross and dot products. But the important part is the quaternion transformation. So if I have a point, which is a pure quaternion, it's a vector. So in order to translate it, I just add a vector. If I want to scale it, I multiply it by a scalar. But if I want to rotate it, then I do the sandwich transformation. So this is the point P, and I want to rotate it. So I take the quaternion of the rotation, Q, and I multiply by Q from the left and by the conjugate of Q from the right. And this will be the result will be the new point rotating. Why is that like this? You can see in the links. It's long to prove it, but this is the main idea of applying such transformation. And if I want to transform it further, so apply another transformation, so I do the sandwich again. So I put another cube from the left and another cube, the conjugate of cube from the right. So I can, like, so I can use transformation one after the another, like rotations, doing rotations one after the other. That's the main idea. Any questions? There's a lot more here, but yeah, a lot more. You can look at this. I want to show just one more thing. So there's the, what happened? Why it's jumping? Two more things. So it uses here quaternions to compute Euler's angles, roll, pitch, and yaw. You can see it by yourself, and from that, computing the rotation matrices. The DCM is the directional cosine matrix. And we can compute DCM from quaternions, and we can compute quaternion from DCM matrix. So there is two-way conversion between rotation matrices to quaternion matrix to quaternion. Yeah. So here, this is the DCM from quaternion, and there was also here quaternion from DCM. Quaternion here, this. Yeah. DCM to quaternion, quaternion to DCM. So it's here, you can look and use it if you want. So also it is used for representing the Earth movement. And I want just to tell you about two very common reference frames. One is the Earth-centered inertia. So it is a reference frame in the middle of the Earth. Very common, but it's not very useful because we are not living in the middle of the Earth. It's just used for transformation. So one very common reference frame is the NED, north, east, down. So X is north, Y is east, and Z is down, like this, something like this. Yeah. And also there's another, kind of the opposite to this is EMU, east, north, up. Very common transformations. Yeah, so that's the whole thing. And if you want to know more, there are the links. Yeah, the links here. And you can learn by yourself. There are very good videos there. They teach much better than me. Okay. So that's it. Now, the question. So with this, I finished the material for the course. And we have your presentations in 2 weeks. Yes, not next week, but the week after. Again, 10 minutes presentation. Everyone must attend. You'll get also a form to fill. And we'll see and learn what you did. That's the idea. If you want, I'll